We'll go ahead and get started. Yesterday we talked about our basic bubble sort. Today we're simply going to cover the next two sorting algorithms that usually come after that, selection sort and insertion sort. And that will then lead us to our, I'll say the standard sorting algorithms people use, which will be quick sort and merge sort, which we're going to cover on Thursday. So today we're just going to focus on selection and insertion sort, and namely how to do these, of course, with our two data structures we have had so far, arrays and linked lists. All right. We already talked about bubble sort, so let's fast forward right there. Now, selection sort. So with bubble sort, you kind of just bubble up by kind of, you bubble up, or the program just bubbles up whatever the top answer is to the top, and then repeat the process until done. Selection sort, you rearrange the list by selecting an element and moving it to its proper position. So, for example, find the smallest, put it at the beginning. Now find the smallest of what's left, put it in the beginning. Find the smallest of that, put it at the beginning. And of course this can be applied to linked list. Let's see if they give us a nice little, no they don't. Okay, great. Well, let's go do it on the board. All right. Go ahead and give me some numbers that are not in any order.
7, 33.
7, 5, 33, 2, 18.
202.
All right, we're going to stop there so I don't have to write too much stuff. Okay, selection sort. We start at the beginning, we find the smallest, and then swap it with the beginning. So, what are we doing?
You have to compare the two values next to each other.
Yeah, so you're going to go through and you're going to find the minimum. What happens to be the minimum? 2. And you're going to swap it with the first element. So the next list, so this is step 0, step 1 would then be 2, 5, 33, 7, 18, 2, 0, 2. All right. So we're done here. We're going to start by selecting here and finding the minimum. What's the minimum? Which one?
5.
5, great. Hey, we don't have to do anything. That's nice. So 2, 5, 33, 7, 18, 2, 0, 2. Okay. We start here. We find the minimum. What's the minimum? 7. All right. And we swap it with which number? All right. All right. Now we're finding the minimum of what part? 33 and forward. And what's the minimum? 18. 18. So what are we swapping?
33 and 18.
All right. Step 4, 5. Whoops. Where's my cursor? All right. Now what do we search?
You compare the 33 and so on.
Yeah. Do we need, what's the minimum? 33, so you swap the 33 to 33, well, that's easy. 2, 5, 7, 18, 33, 2, 0, 2. Okay, great. So, any questions about this one? Good.
Would it compare?
Yeah, that's selection sort. Move it over and repeat, rinse and repeat. Yeah, hopefully, after all the work you've been given, giving you a slight reprieve with work, just doing selection, insertion, sort. Hopefully that's easy. I don't know. Yes?
Would it try and run past 202 and then realize?
No, because once you hit 202, do you have to, if a list has one element, is it sorted? Yeah, you're done. Okay, so how many comparisons were made? How many comparisons were made up here? N minus 1. How many were made down here? 1. Oh yeah, n minus 2, dot, 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 down to 1, right? Okay. All right. So for each line you did in, and how many of these were done? So this time we did n minus 1, n minus 2, dot, 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 down to just 1 comparisons. So how many of these are there? 6, or how many elements? So yeah, so there's been 6, aka n, right? So the idea is that if we extended this out to have length of 1,000, 999 down to 1, and you did it 1,000 times. So what's the big O of this for comparisons? Not quite O of n. How many comparisons were done? So, and on here, what was the average number of comparisons? On average, if you were to sum this up and take an average, how many comparisons were done? Down here was just 1, up here was n minus 1, and you decremented it by 1 each time. How many comparisons were done on average?
N.
N divided by 2 on average. So we'll say n divided by 2 for all of this. And how many times do we do n divided by 2 comparisons? N, right? So multiply by n, which equals, of course, n squared divided by 2, which is equivalent to the big O of n squared. Okay. All right, any questions on this quick analysis? You haven't taken discrete math, so I can't math it out for you, but I'm just going to give you a pictorial explanation for now. Did you understand how to derive this by looking at it or by inspection? Any questions? So comparisons, and that's for comparisons. All right, let's do another analysis. How about swaps? How many swaps were done on this one? 1. This one?
Always 0.
1 or 0. We'll say 0. 1. 1.
0.
That was technically 0. Okay. So you're either doing 1 or 0 swaps. How many times do you do a swap? N times. So it's n times maybe 1 or whatever, which makes the number of swaps what? O of? Yeah, someone said it. O of n. So swaps equals O of n. Anyone remember what the bubble sort numbers were?
Like,
Yeah, for comparisons, it was still n squared because it did the same thing. But how many swaps were done? A lot more. It was actually not O of n, it was O of n squared. So selection sort right now at least beats it in swapping because you only have to swap O of n times. Okay. Any questions on this analysis before we move on? All right. Okay, so they did their own analysis. So swap does 3 assignments, executed n-1 times at worst. So they called it O of n for swapping. We came up with that. And then for find min location, which is what their function used, and that was to find the minimum element. It took k-1 key comparisons, executed n-1 times. You math it all out, and you get basically O of n squared, which is what we just did just now on the board. Okay, insertion. So, any questions on selection sort? It's going to be a fast lecture today, guys.
Is it better than bubble sort? I just like, how much better is it than bubble sort?
That is a great question. Can anyone answer that?
A lot better.
A lot better, maybe.
Well, I guess that was because, not because the O of n's were the same. I mean, and to the
Into the second power. Yeah, you can say it that way.
okay, for the comparison, but you said for actual
Swapping.
swapping of the numbers?
Mm-hmm. Big O. What was bubble sort? Let's go back. Bubble sort, comparisons. Do we do sorting? It didn't tell you the swapping.
It's an n squared.
Yeah. Number of assignments, right. Again, n squared as well. So bubble sort's n squared for both swapping and comparisons. So which of these two algorithms is better from a performance standpoint? Selection sort. Okay, great. Okay. How would you implement this? I think y'all can look at it how you'd implement it on an array. You'd find the minimum location, then do a swap. How would you implement it with a linked list? Yeah, you have to have a rover. You have to keep track of your previous. Yeah. You have to keep track of your once you find the min, you need to keep track of your previous. And you need to keep track of where you're where you're starting, so you know to have the 33 jump over here, and then link the 2 to jump over here, and move the 7, of course, as down as well. Little frustrating. So that's why a different sorting routine was also they came up with that was still simple and very similar performance-wise to this, and it was called insertion sort. So I'm going to go and pause the video, and we'll talk about that.